Hello and welcome to this GeoStudio Material Model webinar series on modified CAM clay. My name is Catherine Dompierre and I am a Research and Development Engineer with the GeoSlope Engineering team here at Sequent. Today's webinar will be approximately 30 minutes long. Attendees can ask questions using the chat feature. I will respond to these questions via email as quickly as possible. A recording of the webinar will be available so participants can review the demonstration at a later time. GeoStudio is a software package developed for geotechnical engineers and earth scientists comprised of several products. The range of products allows users to solve a wide array of problems that may be encountered in these fields. Today's webinar will focus on Sigma W. Those looking to learn more about the products, including background theory, available features, and typical modeling scenarios, can find an extensive library of resources on the GeoSlope website. Here you can find tutorial videos, examples with detailed explanations, and engineering books on each product. To begin this webinar, let us consider a soil element using both the experimental approach and a numerical approach. In an experimental approach, there's a real soil sample that is used, for example, to conduct a triaxial test. The responses of this soil sample are measured in the laboratory and the soil behavior can be studied accordingly. In the numerical approach, on the other hand, it is necessary to perform a calibration process for the constitutive model as the first step of numerical modeling. The measured results from the soil sample are required at this step. This calibration procedure provides model constants for the soil. These constants are then used as input parameters for a numerical model, for example in Sigma W, and the simulated results will be obtained by solving the numerical model. The simulated results can then be compared to the corresponding laboratory results to verify the accuracy of the numerical modeling. In today's webinar, the calibration procedure for the modified CAM clay material model will be provided. This process will be applied to a specific type of clay, as an example, and the numerical values of the model constants will be calculated. The main steps of modeling a triaxial test in Sigma W will be reviewed. And the simulation results will be compared to the experimental and analytical results for validation purposes. This webinar will begin by reviewing the theory of the modified CAM clay constitutive model. Then step-by-step instructions will be provided for calibrating this material model using a triaxial data series. A demonstration of the steps of modeling a triaxial test in Sigma W will be provided, and the simulated results will be compared and verified using the analytical and laboratory results. The modified CAM clay material model is a critical state-based, nonlinear constitutive model developed by Roscoe and Berland in 1968. In this model, the authors modified their previous constitutive model by changing the geometry of the yield surface from a bullet-shaped surface to an ellipse. For an isotropic loading condition, where the stress path is entirely located on the horizontal axis, the plastic strain increment vector is also horizontal. Note that the plastic strain increment vector is perpendicular to the yield surface. The soil state is overconsolidated before reaching the yield surface. After that, the elliptical surface will be scaled up as loading progresses. The soil undergoes normal consolidation in this phase. The soil response is assumed to be linear in V versus ln P prime space. The slope of the normal consolidation line is called the virgin compression index, or lambda, while the overconsolidation and unloading-reloading lines are assumed to be parallel. Their slope is called the swelling index, or kappa. In a deviatoric loading condition, where the vertical principal stress is different than the horizontal one, the stress path reaches the elliptical yield surface at a point away from the horizontal axis. This means that the plastic strain increment vector contains deviatoric components as well. In V versus ln P prime space, the overconsolidation and unloading-reloading phases are still aligned with a slope of kappa. However, the normal consolidation phase is not necessarily a straight line for a general anisotropic loading condition. Before moving on to the demonstration, we need to review some fundamental formulations. As mentioned before, the modified CAM-clay material model is a critical state-based constitutive model, so different stress paths eventually tend to the critical state line. In this model, the slope of the critical state line, or the critical state stress ratio, can be expressed in terms of the effective friction angle in the Moore-Coulomb failure criterion. The yield surface is an ellipse that passes through the origin and intersects the critical state line at its peak point. The overconsolidation ratio is the ratio between the maximum isotropic stress experienced by the soil and the current isotropic stress of the soil. For a stress state inside the yield surface, the soil response is elastic. The compliance matrix is diagonal, and the bulk and shear moduli are both proportional to the mean effective stress, P', and the specific volume, V. After reaching the yield surface and as it expands, the soil response becomes elastoplastic, and non-diagonal coupled components appear in the compliance matrix. Incremental strains in this condition are the summation of elastic and plastic strains, and so the current stress ratio plays a key role in the soil response. According to the framework proposed in the modified CAM-clay model, the model constants include the slope of the normal isotropic consolidation line, represented by lambda, the slope of the overconsolidation line, or kappa, the effective Poisson's ratio, mu prime, and the effective critical state friction angle, phi prime. These four constants determine the soil type based on the modified CAM-clay model. Some other parameters will also be needed to describe the initial conditions of a specific soil sample. These include the initial void ratio, the unit weight, and the overconsolidation ratio. In order to find the model constants corresponding to a specific soil, a step-by-step calibration procedure is discussed here based on drain triaxial test results. As the first step, the critical state stress ratio, M sub C, or its equivalent, the effective critical state friction angle, can be estimated from drain triaxial test results. According to critical state soil mechanics, stress paths of samples with different initial confining stresses eventually tend to the critical state line at their failure point. Therefore, the critical state line is a straight line that passes through the failure points. The critical state stress ratio, MC, is the slope of this line. This constant can be calculated using the method of least squares. Since the failure criterion in the modified CAM-clay model is the same as the Moore-Coulomb model, the effective critical state friction angle, phi prime, is not independent of the critical state stress ratio, MC, and can be expressed directly in terms of it. To demonstrate the calibration procedure, let us consider three drain triaxial compression tests on Bothkener clay that was conducted by McGinty in 2006. These three tests have been performed at different confining pressures. The deviatoric compression stress in these tests continued until failure was achieved. The critical state line that passes through the failure points in P' versus Q space has a slope of 1.36. Thus, the critical state ratio MC is 1.36, and consequently, the effective friction angle is calculated to be 33.7 degrees. The second step of the calibration procedure is to estimate the slope of the overconsolidation line, or kappa. For an overconsolidated soil, kappa is the slope of the overconsolidation line and represents the elastic response of the sample. The trends of the measured values of P' and V in this branch of the graph can be projected to a straight line. The slope of the y-intercept of this line can be calculated directly using the method of least squares. An alternative method for estimating kappa is to use the corresponding parameters measured during an unloading-reloading process. For a normally consolidated soil, the unloading-reloading process is required for estimating kappa. The method of least squares can again be used to calculate the slope and the y-intercept of this straight line. Let us apply the second calibration step to the example triaxial test results on Bothkaner clay mentioned earlier. The overconsolidation branch in each of these three curves is projected to a straight line. The slope of these three lines is almost the same, so their average 0.084 is used as the constant kappa for this type of clay. In the third step of the calibration procedure, the slope of the normal isotropic consolidation line, or lambda, will be estimated. It should be noted that lambda is the slope of the normal consolidation line only in an isotropic loading condition. For other loading conditions, however, the normal consolidation branch in V versus ln P prime space is not necessarily linear, and so the slope of its curve is obviously not equal to lambda. Based on the modified CamClay framework, it can be proved that there is an alternative space in which the sample response is linear even under normal consolidation. The x and y axes in this space are functions of the measured parameters and constants estimated in the previous steps. The overconsolidation and unloading-reloading branches are both horizontal in this new space, and the normal consolidation branch is a straight descending line. The slope of this line represents the difference between the isotropic normal consolidation slope, lambda, and the overconsolidation slope, kappa. Given that we already estimated kappa in the previous step, the constant lambda can be found by applying the method of least squares on the proposed space. As shown in this figure, the data points corresponding to three example triaxial tests are plotted in this alternate space. The average value of the slopes of these three curves in the normal consolidation branch indicates the difference between lambda and kappa. Since the value of kappa was previously obtained as 0.084, the constant lambda is estimated here to be 0.332. The fourth step of the calibration procedure is to calculate the overconsolidation ratio for each soil sample. To do this, it is required to recognize the mean effective pressure in which the response of the sample changes from the overconsolidation condition to the normal consolidation condition. Let us refer to this pressure as the yield pressure, or P'(y). The overconsolidation ratio, however, is the ratio between the isotropic preconsolidation pressure, P'(C), and the isotropic initial pressure, P'(0). As stated earlier, the response of the soil changes from an elastic or overconsolidated state to elastoplastic or normally consolidated state, only if its stress path touches the yield surface. As a result, for a stress path that is not necessarily isotropic, the yield pressure P'(y) is less than the isotropic preconsolidation pressure P'(C). These two pressures, however, are not independent. For example, in a drain triaxial stress path with a slope of 3:1, the deviatoric stress at the yield surface is 3 times the difference between the yield and initial pressures. So the isotropic preconsolidation pressure, P'(C), can be expressed in terms of yield stresses using the yield function of the elliptical surface. Finally, the overconsolidation ratio is estimated as a ratio between the isotropic preconsolidation pressure, P'(C), and the isotropic initial pressure, P'(0). This approach is applied on the Bothkaner clay triaxial test data to estimate the overconsolidation ratio for each of the 3 samples. First of all, the yield points of the samples in V versus ln P prime space are detected. The values of P'(y) for tests A1, A2, and A3 are about 83, 107, and 179 kPa, respectively. According to these yield pressures, 3 yield surfaces are drawn, and the isotropic preconsolidation pressures for 3 samples have been estimated as 115, 120, and 201 kPa, respectively. With this, the overconsolidation ratios for the samples are found to be 2.069, 1.224, and 1.339. Therefore, the first sample is more overconsolidated than the other two samples. This can also be deduced from the response of the sample in V versus ln p prime space, where it has a longer elastic branch than the other samples. The last step of the calibration procedure for the modified CAM-clay constitutive model is to determine the effective Poisson's ratio, mu prime. Poisson's ratio is defined as the ratio of the change in the element's radial strain to the change in its axial strain in a drained test. In the modified CAM-clay model, the Poisson's ratio is considered only for the elastic or overconsolidated condition, and its value is assumed to remain constant during loading. Consequently, in a drain triaxial test, the method of least squares can be applied on the purely elastic or overconsolidated part of the curve in radial strain versus axial strain space to estimate the value of the effective Poisson's ratio. Let us apply this final step to the Bothkner clay triaxial test data. The yield points of the samples have already been detected in the previous steps and are marked with an X in these figures. As can be seen from the figure on the right, the sample response in this space is almost linear before reaching the yield surface, while nonlinear behavior begins after yielding. If the linear response of all three samples was approximated by only one straight line passing through the origin, the slope of that line would be approximately 0.353. This value is an estimation of the effective Poisson's ratio of the Bothkner clay. The results of the calibration procedure for the Bothkner clay can be summarized as follows. 4 model constants have been estimated, including the slope of the normal isotropic consolidation line, the slope of the overconsolidation line, the effective Poisson's ratio, and the effective critical state friction angle. In addition, the sample-specific parameters for these 3 tests include initial void ratios, which were measured directly in the lab, and overconsolidation ratios, which were estimated in the calibration procedure. These constants and parameters will be inputted in sigma W using the modified CAM-clay material model. Now that we've reviewed the step-by-step calibration procedure for the modified CAM-clay material model, I will describe how to model a triaxial test in sigma W and compare the numerical results with the previously mentioned laboratory data. The numerical model configuration is based on the geometry and boundary conditions of the triaxial test conducted in the laboratory. A typical triaxial test sample has a cylindrical shape with a diameter of 5 centimeters and a height of 10 centimeters. Due to the axisymmetric shape of this geometry with respect to the central vertical axis, we can use the 2D axisymmetric geometry type in sigma W. The geometry is also symmetric with respect to the horizontal axis, so I will only model the top half of the triaxial sample. An 8-node single-element model is considered for the resulting rectangle. The left and bottom sides of this model are fixed in the x and y directions, respectively, while loads are applied to the other 2 sides. The next step for setting up our sigma W analysis is the material definition. This step is performed in the Define Materials dialog. The material model is set to modified CAM-clay. The sample parameters, including the initial void ratio and overconsolidation ratio, are entered as discussed earlier. It should be noted that the effect of the soil's self-weight can be removed by setting the unit weight to 0, while the K0 effect can be deactivated by specifying K0 NC as 1. Lastly, the constitutive model constants are entered based on the results from the calibration procedure for Bothkner clay. The simulated triaxial models are then loaded under first, the isotropic confining pressure, and secondly, the deviatoric pressure. Thus, there are 2 sigma W analyses required for each of the triaxial tests. The confining pressure analysis acts as the parent, and its results are used as the initial data for the displacement-controlled deviatoric analysis. These conditions are established using the boundary conditions specified in the Define Boundary Conditions dialog. For example, in test A1, the constant normal stress of 58 kPa is applied on both the right and top sides of the model using a normal tan stress boundary type for the confining pressure analysis. In the deviatoric analysis, a displacement type boundary condition is applied to the top of the model. A displacement of 2 centimeters, that is equivalent to 40% strain, is applied linearly over time using a spline data point function. All the analyses are then solved in sigma w, and the stress, strain, displacement, and other responses of the model can be extracted and interpreted. As shown here, a 2D axisymmetric geometry is used to set up the model domain. In the 2D view, only 1/4 of the cross-section running through the center of the triaxial sample is modeled, given the symmetry of the domain. In the analysis tree, there are 3 sets of analyses, each representing a triaxial test conducted on the Bothkner clay samples. In each test, the confining phase is the parent analysis, and the deviatoric phase that uses the results of the previous phase is the child analysis. The material properties for 3 soil samples were obtained using the outlined calibration procedure. The materials are specified in the Define Materials dialog. The same type of clay was subjected to the triaxial tests. Therefore, the constants of the modified CAM clay model are similar for each sample. However, the initial void ratio and overconsolidation ratio are not the same for each sample, and so 3 different materials were defined. An isotropic elastic material was used during the first phase of the triaxial simulations because the nonlinear stress-strain response is inconsequential to establishing the initial stresses. The accumulated displacements and strains are reset at the start of the loading phase of the simulation. The 3 isotropic elastic materials defined here are applied to the corresponding confining analyses. The defined modified CAM clay materials are applied during the deviatoric portion of the triaxial test simulations. The boundary conditions representing the confining pressures and deviatoric strain are specified in defined boundary conditions. 3 constant confining pressures were created for the 3 triaxial tests using the normal tan stress boundary type. These boundary conditions are applied to the corresponding confining analyses. The deviatoric strain boundary for the displacement control loading phase of the triaxial test uses the force displacement boundary type, with the displacement function defined such that displacement increases over the deviatoric strain analysis from 0 to 2 centimeters. Before solving an analysis, the final step is to review the finite element mesh. In the Draw Mesh Properties dialog, we see that the global element mesh size is 0.05 meters. Thus, the model domain represents 1 element. This analysis has already been solved, so I will move to the results view. I will go to the first deviatoric analysis to investigate the results. In the Draw Graph dialog, I have created graphs to illustrate the stress path, stress-strain curve, and void ratio versus mean effective stress. I can click through the different analyses to view the results from each. Let us now compare these results with the analytical solution and also with the corresponding laboratory data. The different simulation results of test A1 are compared here with the corresponding laboratory results. Discrete scatter points represent the laboratory results, and the continuous black lines are the sigma W simulation results. Analytical results for the modified CamClay model are also shown in these diagrams as orange dashed lines. The full compatibility of the analytical and numerical curves shows the reliability of the implementation process of this material model in sigma W. When comparing the laboratory results with the constitutive model simulations, some of the plots show a better fit than others. For instance, a very good match can be seen in the first curve, where the data in V versus ln p prime space is simulated by the modified CamClay model. However, the results from test A1 in some of the other spaces do not match as nicely as the first curve because of the very nature of calibration. The calibration procedure highlighted in this webinar required multiple samples, which each have varying degrees of disturbance. For example, during the calibration process, the best fit line that was used to determine MC was below the A1 and A3 data points, but near the A2 data point. Thus, the simulated deviatoric failure stress was underestimated for the A1 sample. Meanwhile, the simulated deviatoric failure stress better correlates to the laboratory results from test A2 and underestimates the deviatoric failure stress for test A3. This demonstrates the nature of the calibration process. However, as mentioned for the first test, the analytical and numerical results show a perfect match, verifying that sigma W accurately represents the modified CamClay material model. In this webinar, the calibration procedure of the modified CamClay material model was provided in 5 straightforward steps. The results of the drain triaxial test were the only laboratory dataset required for calibration. The identified material constants were used in a sigma W numerical model, and the simulation results were found to compare favorably with both the analytical solution and corresponding laboratory results. Here are the references discussed in this webinar. We have now reached the end of the webinar. A recording of this webinar will be available to view online. Please take the time to complete the short survey that appears on your screen so we know what types of webinars you are interested in attending in the future. Thank you very much for joining us and have a great rest of your day. Goodbye.